Good morning, Srini. How are you?
Hello, sir.
How are you?
Hello.
Yeah. I'm asking you, how are you?
I'm fine, teacher.
Okay, where is your teacher now?
Oh, he chapter 3, but no. This week no school, what, teacher? All holiday only.
Oh, 2 weeks is it?
3.
Oh, 3 weeks holiday. Okay,
This
okay,
is the first week, and then another 2 more weeks. So got
okay.
still more
We
time
are
to study
starting
sem
the
1
new.
lunch.
I'm using my old laptop, so the sound system is not that good. So I got problem that
Okay.
right? The recording is also not very good. So let me
It's okay, sir. I can hear.
can hear, but the voice is very poor in the recording.
It's okay, sir. I can hear.
I know you can hear about the recording, so be careful.
Okay.
Okay, let's start a new topic. Topic 3 or 21. Let's make a start. We will try 1.5 hours today, if we can,
Today, okay.
because I owe you half an hour.
No, but you said the yesterday one cancelled, right, teacher?
Yeah,
Remember?
but still owe you half an hour.
Okay.
So you don't want the half hour to dangle there. Why is it
Yeah.
taking
Okay.
too long? Yeah.
Teacher,
Yeah.
you think I can do it at the sem 1?
Say again.
You think I can do it at the sem 1?
Someone is elementary. The reason why you didn't do well, as I said to you, I be honest with you. You didn't
Yeah.
put in the effort. You come
Oh.
for tuition, you hope the tuition will help you, it won't help you, right? And then you give
Mm.
excuse of phobia. It's not phobia. The book that you have is quite good. If you look at the question, you don't know how to answer, go and look at the
Look at
question
the
back there. Look at the back there, how to answer. You got a
answer.
yeah.
The
You can ask your tutor, no, I'm here to help you, but you are not doing that, right? You are not making an effort to learn. That's why you are struggling. You know what is happening, why I can't, okay. So it's really up to you, right? That's why this semester I also worry for you. If you don't bother to put in the effort to study, to give the excuse of phobia, I think you will have problem. Okay, as I say, look at the question. If you are lost, look at the answer. The book has given you the answer, and that will guide you. And if you still cannot, then ask me in class. That's why I'm here to help you. So it's really
okay.
your how you want to do, how well you do is really up to you. I can't do anything, right? I'm
Mm.
learning, teaching you. I have to learn. I have to work out the question, answer the question. That's why I'm learning. Except you are not. Okay, let's go to 21. Sound waves. Propagation of sound waves. Sources of sound. Sources of sound. Intensity level of sound. Right? We'll try to cover 21.1 and 21.2 today. We use some of the time for you to do some work. Why is it not responding to me? Right, then we go to beats 21.4. Then we go to Doppler effect. Right, that probably will be next week. These three topics will be next week. Okay, let's make a start. Since your teacher has taught you, you should try to do the checkpoint after your teacher has taught you. That's how you are going to improve. So you should start revising your term 1 already. Don't wait for the end. So that's your book that we are using. And we are now on page Page 79. Okay, as far as syllabus is concerned, propagation of waves, of sound wave. Looking at sound wave for this part. Explain the propagation of sound wave in air in terms of pressure variation and displacement. Right? How the pressure and displacement vary with distance. Interpret the equation for displacement. So basically, we are just looking at these two equations now. Then use the standing wave equation to determine the position of node antinodes for standing wave along stretch string. So this one we are done already, under 20.4. Okay. Okay. That's the picture of how sound is propagated. There's your loudspeaker. The diaphragm moves to and fro. As it moves to and fro, the air particles being forced to vibrate. And that's the direction of travel of the wave. The direction of vibrating. The arrow show you the vibration. And that is the how the pressure changes with distance. Right? This is just your ideal gas equation. Right? Pressure, if we consider in a box the ideal gas as the pressure, so it can roughly give you some idea that pressure, besides depending on the uh, mean square speed, it also depends on density of the air, right? Or density of the medium. Having problem controlling it. What is happening? Right? Sound is mechanical wave. That's important to remember. It needs a medium, requires a medium for propagation. Without a medium, it doesn't propagate. A medium can be solid, can be liquid, can be gas. It can travel to gas, liquid, or solid. Propagation of sound in medium creates pressure variation. That's the sound wave pass through. It's the pressure in the medium or the air that's changing. Propagation of sound in the medium may be studied as variation of displacement or pressure. Right? You can study as how the displacement change with distance or how the pressure changes with distance from the source. Sound waves. Right? Sonic are sound waves that we can hear. And we can divide the sound wave into those that we can hear. Audio, right? The frequency that we can hear is 20 hertz to 20 kilohertz. Ultrasonic are high frequency sound wave beyond the range of human ear. Usually we take about 18 kilohertz. Those sound wave greater than 15 kilohertz. Speed of sound is about 330 meters per second. Right? Depend on the pressure. Okay, that's just for your info. Comparing water wave, sound wave, and light wave. Ripple tank experiment. Our speed of the wave is about 0.12 meters per second. Sound wave is about 300. We say 330. Light is 300. 3 times 10 to the power 8. You can see the light wave, very high speed. Frequency wise, it's about 6 hertz for ripple tank. For sound wave is 20 hertz to 20 kilohertz. Whereas for light, is 3.8 to 7.5 and 10 to up to 14 hertz. Very high frequency. Right? The one that we use in the lab for ripple tank is very low frequency. Wavelength for ripple tank is 0.2 meter. For sound wave is 15 to 0.015 meter. For light wave, it's very small, between 4 to 8 and 10 to the power minus 7 meter. Right? Very small wavelength for light. High frequency, high speed, but low wavelength. Right? Just for info only, nothing much to remember. Frequency of light is much larger than frequency of sound. Wavelength of sound is much longer than light waves. And look at the wavelength of sound that we encounter. Compare with the wavelength of light. It's very long from sound. Okay, how we produce sound in the laboratory, in the physics lab. Right? We have audio frequency oscillator. This is a source of alternating current where we can change the frequency. That's a loudspeaker. To detect, we use microphone and then CRO. Audio frequency oscillator provides the sinusoidal varying voltage or alternating voltage in audible frequency range. We call it audible audio because it is something we can hear. Loudspeaker converts the varying voltage to sound waves. That's a loudspeaker. Microphone converts the sound wave to alternating voltage. That's how you detect microphone there. CRO display the alternating voltage. Propagation. Sound waves are longitudinal waves. Sound waves travel through air as a series of compression and reflection. That's a compression. That's a reflection. As compression, region of high particle density or high pressure. Okay. High particle density or pressure. Particles near a compression are displaced towards it. Okay. Compression there. Particles are all moving towards it. And reflection, there's your R, reflection in between there. Reflection. Okay. There's a compression. Reflection are region of low particle density, low density or low pressure. Particles near a reflection are displaced away from it. Okay, remember, particles are displaced away from it. Okay? Particles are moving away from the reflection. Okay, let us look at what is happening, compression and reflection. This is the particle at rest, right? Where there is no wave, no sound wave passing through it. Yeah, you can imagine they are in equilibrium position. And when the sound passes through, right, you can see that this part there is moving to the left. Reflection is not moving. Compression is not moving. Compression is 0. Reflection also at rest, not moving. But the one to the left, it is moving. Amplitude moving to the right. One here is not moving. Compression. The one here, this part there, moving to the left. So we must have a system of convention. We must taking outwards as positive. This one outwards as positive. And taking to the right as positive. This one moving to the right as positive. This one moving to the left is negative. There's a convention. So in this case, let's carry on. At compression and reflection, the particles are at 0 displacement. Yeah, compression, reflection. Remember, compression is here. If you look at this compression, the particles to the left is moving towards it. Positive, this positive, positive to the right. And then the particle here, this particle is moving towards it also. To the left, negative means to the left. Now you look at the reflection, this part of the reflection, the particles are moving away from it. That one you must be able to recognize. Particles are displaced towards a compression. That's what we are saying. Compression, particles are displaced towards it, but displaced away from a reflection. That's the reflection. Particles are away from it. Right? Must recognize the displacement Displacement, sorry, this should be distance, not time. Let me just change that. Taken for internet. This one. Ask me to draw will be too troublesome. Okay, so that is your time. And time or displacement doesn't matter, like still more or less the same thing. Okay, so let's carry on. Any question you want to ask?
Not yet, teacher. Oh, teacher.
Yeah.
So just say the amplitude is negative, right? It's on the down curve, so it goes left. Correct.
Say again.
If the amplitude is negative,
Okay.
going down curve, that means the arrow is going to the left. Correct.
Negative, we must always have a convention. Upwards, this upwards is positive. Right? So how do we show it in longitudinal way? Right? We must take to the right as positive. So this is upwards.
Yeah.
So it means that this is to the right.
Oh.
Right? This one is downward, negative. So it's moving to the left.
Yes.
C is here. So you must be able to recognize negative slope is where you find your C. Positive slope, right, at the zero displacement is where you find the R. Okay?
Oh. No, but why is it at zero, teacher?
It's not moving. It's stationary.
Oh,
The
because
other to the
it's
left
at
and right are vibrating.
zero displacement.
Compression and reflection, the particles are not displaced.
Oh, that means our
They are all
negative
at
and
different displacement to the left and right. The largest is
ah,
here. Largest is here. Right? This one didn't show you everything. It just show you this part. Right? The largest one is here. There are others here.
okay.
Smaller displacement or nearer or compression, also smaller displacement. Right? Smaller still displacement as well. Okay.
Okay.
Right? Correction to your book. Right? Your book draw it this way, which is completely wrong. Right? The diagram given in your book is completely wrong. You have to adjust it slightly. Right? Adjust it that way. Figure 21.2, page 79. Right? To adjust it that way. Where there is this one, high pressure above atmosphere. Right? This is pressure changes. This is atmospheric pressure. Atmospheric pressure. Call atmospheric pressure at zero, but this P now is the pressure changes. Right? You should put delta there to show it's the pressure change. Okay, compression, high pressure. Rarefaction, low pressure. Okay, right? So you will probably have to adjust that. So you can look at the from maximum to maximum. You can look at from compression to compression is a wavelength, or from rarefaction to rarefaction is a wavelength. I don't know. Okay, sorry that the wavelength is slightly different, right? Because of the changes there. The diagram have to cut it and redo it. So just make a note lah. At compression, the pressure is above atmosphere. Right? The air is, if there's no sound, it's atmospheric pressure. When there's sound passing through at a compression, the pressure is above, higher pressure, because all the particles are going through a compression. So at rarefaction, the pressure is lower because most of the particles are moving away from it. So pressure is lower than the atmospheric pressure. Okay, this is what I try to do. This is a displacement time graph. This is where it is at rest, no sound passing through. So when sound passing through, this can think of this as layer of air. As the sound pass through, this one is moving to the right. Right? This one is not moving. This one is moving to the left. Right? And this one also moving to the left. Slightly greater displacement. Right? Very hard to show. Reflection is not moving. This one is moving to the right. This one is moving to the right. This one is larger displacement, smaller displacement. So that is your compression. Okay, so that's roughly to show you, right? Not easy to show. Okay, so that is your displacement distance graph. This is your air pressure distance graph. Particles at rarefaction and compression have zero displacement. That's why we have said they are not moving. They are stationary. From a compression to another compression is a wavelength. That's what we say. Compression to compression is a wavelength. From compression to a rarefaction is half a wavelength. Compression, rarefaction, half a wavelength. From here to here, half a wavelength. Or you can take it from here to here, half a wavelength. Depending on which graph you want to look. You look at pressure changes or displacement with distance. Displacement to the right is positive, but to the left is negative. Remember that. Phase difference between pressure and displacement is half pi radian. That means displacement leads pressure. Okay? Displacement come first, 0 come first, compared to this 0 is 90 degrees. Right? Or you want to look, can look at the maximum point. Maximum point. Right? The angle difference is 90 degrees or half pi radian. Any comment? Let me digest. Say you have
Oh, from a compression to another compression is a wavelength.
that's right. Or from high pressure to another high pressure is a wavelength.
Okay.
Right? Compression is always the highest pressure, maximum pressure. Rarefaction is the lowest pressure.
Rarefaction is the R, right? So,
Rarefaction is R. Compression is the C.
oh, that's why half a wavelength and then C to C is wavelength lah.
Our wavelength is from compression to rarefaction.
Yes.
Okay, make
From
sure you
compression to
review.
compression means wavelength.
After I teach you review, then go to checkpoint.
Okay.
Cannot always give excuse phobia. I know how phobia is like. When I was your age, I don't know how to do it. I look at the answer, I don't look at the question, I don't know how to answer because you give only answer nor model answer. Whereas your book is very good for model answer. You cannot do it, look at the answer, understand, and then try to do it yourself without copying. Okay. Right. So this is another diagram to show you. This dotted line is the atmospheric pressure. And then this is the increased pressure and the compression. Right? Decreased pressure, the rarefaction. Right? So the air particles are vibrating to the left and right. This one is all the particles vibrating towards the compression. You can find it in the internet, a lot of things there. So sometimes it may be wrong. Picture may be a bit wrong. Okay. Okay, variation of pressure and displacement with distance. Okay, we can redraw that. There's a displacement distance graph. There's your atmospheric pressure when it's not moving. And that is your pressure, atmospheric pressure plus P naught. P naught is the amplitude of pressure. Atmospheric pressure minus your P naught. Pressure is highest at compression. You can rewrite that. P max. This is maximum. It's atmospheric pressure plus your P naught. P naught is the change in pressure. P atmospheric pressure is atmospheric pressure. And this is the amplitude of change in pressure, P naught. Pressure is lowest at reflection. Remember, there's a reflection.
Yep, correct.
Right? Okay, I can write P min. There's your P min. Atmospheric pressure minus your P naught. Okay. You saw in your book. I said that there are some steps missing as well. I'm just pouring your book, go to see. Okay, this is what we have done in example 20.1. In case you've forgotten, phase different. Right? You should be able to write, recall. V1, you should be able to write the equation. If the amplitude of the wave is V0, then the equation for V1, should be able to write equation for V1, V0 sine omega t. Then V2 should be able to write. Right? That is 45 degrees. It's shifted by 45 degrees. That's 45 divided by 180 times pi. Or if one, you can write 360 and then this 2 pi, same thing. Calculate out 554 radian. So it's shifted to the right. As remember already, we have gone over with you already. Shifted right is negative. And replace that is the equation. Shifting to the right, that is your phase, that angle there. Right? So you write as minus pi over 4. That's all. Okay. I'm just reviewing with you. You've seen your last week's lecture. Okay. Now let's apply that to pressure, variation, and displacement. Right? Pressure is given as that. Atmospheric pressure plus change in pressure. Atmospheric pressure, change in pressure. Right? So change in pressure, which is this axis, is just your P minus P atmospheric pressure. We're just taking the atmospheric pressure across there. Right? For this graph there, displacement distance graph, this is your Y, this is your X. Okay? Distance is your X. I can write as A sine omega t minus your kx. And there's your theta if you like. Right? Pressure, change in pressure. Right? It's the same graph, except now the sign is being shifted to the right. Okay, so you can recognize this become a cos graph. So it's minus P naught cos omega t minus kx. Okay, if not, alternative equation would be right, P naught. Right, there's your theta. There's your theta still there. Right, but it's shifted to the right by this is pi over 2. Right, pi over 2. That's why we get that. Okay with that so far? Okay. Let you digest for a while. Right, that is pi over 2. That one shifted to the right pi over 2. That's why we write pi over 2. Right, that's your theta.
But then the negative P naught cos, and then you change
Negative,
into
that's
P
all.
naught sine.
Negative means shifted to the right. Positive means shifted
Yes.
to the left.
Yes.
Right? It's important. You must review. You must do your homework. If not, you will keep on asking me the same question. I'm making it easy for you. I didn't expand. Didn't use any maths. You can expand this one. Expand this one. You get this one back. Which I'm not going to do that. You keep on asking me the same question. You can go back to your maths. I show you my physics way easier to understand. Okay. Sound wave need a material medium. Sound wave travel in gas by adiabatic compression and refraction. Refraction is like tension, compression, refraction. Speed of sound in an ideal gas is given by the formula. Okay, it's not mentioned in your syllabus. Right? Don't worry about how you get it. Just remember, it depends on absolute temperature. So R is your gas constant. T is your absolute temperature. M is your molecular mass. Right? It's not isothermal compression. It's adiabatic. That's why you need your gamma. Right? Gamma is your first semester work. It's just the ratio of the molar heat capacity, constant pressure, constant volume. In liquid and solid, the speed depends on elasticity and density of the medium. Speed of sound in solid is largest, followed by liquid and then gas. Right? For solid, this is Young's modulus, this is the density. Okay, that's the density of the solid. For liquid, it's the same lah. Liquid, the speed also don't think you need to go that detail lah. Right? For liquid, this one we use a different modulus lah. Right? That you don't need to, that you didn't learn in your first term. This one the same thing. Right? For gas, also we use a different modulus called I think it's called bulk modulus. Okay, which is not in the syllabus, so we won't go too far. Right? This is just for general knowledge. So we have more or less completed. You need to know what is the compression. You need what is audio frequency. You need to know the sound wave is non-linear waves. You need to know rarefaction, what is rarefaction, region of low particle density. And then the displacement leads the pressure by half pi radian. And then the equation for displacement distance graph. Then the equation for change in pressure. Right? Either one of the equation. Okay, let us go to checkpoint. You can try the problem. You try to solve some problem in class since you hardly do your homework. Okay, so these are all the things that we need to know. Discuss how the speed of sound in gas is affected, if any, by pressure, temperature, and type of gas. Okay, any comment? Discuss how the speed of sound in gas is affected, if any, by pressure? Not affected by pressure, because as the pressure changes, the density will change. Right? This is the atmospheric pressure. If the atmospheric pressure changes, the density also will change. So you're not affected. Temperature, yes. Right? Speed depends on the square root of temperature. Okay. Refer to your note. Go to your book. How about type of gas? T is absolute temperature. Type of gas, yes. Depends on M is your molecular mass of the gas. Depends on your square root of root M. Okay. Copy down. Make sure and make an effort to copy down. Don't take it too comfortable. I give you everything. I record everything for you. Now you don't write it down. Write down. That's your way of forcing into your head. You have to help yourself. Right? You need to reinforce it. Whatever you learn, need to reinforce it. That's how you remember it. Okay. Any comment?
No, sir.
Okay. Let's do. And number 2. The figure shows a loudspeaker. That's a loudspeaker connected to a frequency generator. It's a frequency generator. The sound of fixed frequency is emitted from the loudspeaker, and air particle P is in front of the loudspeaker. So air particle P. With the aid of diagram, describe the motion of particle P. Okay. How to describe? Yep. Đấy, drawn for you already. It's drawn for you already. This longitudinal wave, that's how it described. It's vibrating. There's direction of vibration. There's direction of travel of the wave. That's all. Particle P vibrates parallel to the travel of wave. Okay, describe the change in motion of particle P when the sound wave is increased. Amplitude of sound wave is increased. Yeah, any comment?
Raja?
No comment. Right, amplitude of increases. Right, amplitude of sound wave increase. Amplitude must increase because it's the sound
Because
wave.
it's going to the right.
To the right and to the left must increase.
Oh.
How about frequency?
Not affected.
Frequency of vibration increases.
Oh.
Right? Just like motion or wave in the string. If I change the frequency, I change the frequency of the wave. Same thing here. If the frequency increase, yeah, the frequency of that increases, this one will vibrate faster. Right? Greater frequency. So the frequency of the sound wave will also increase. Okay, copy whatever you copy in your book. Speed of sound is 340 meters per second. What is the range of frequency of sound detectable by a person with normal hearing? Yep, we have gone over that. So you should be able to tell me. It's not in your book. Can you remember? Right? 20 hertz to 20 kilohertz. That's the audio frequency range. Now go and calculate maximum and minimum wavelength. Your speed is given. You should be able to tell me. Go and calculate now. Give you time to calculate. To force in the formula that you should use. Okay, what formula to use? Ken, Srini, what formula to use? You got frequency, you got speed. You want to calculate frequency. What formula to use?
Frequency, then speed.
Yep, what formula to use?
V equals to F lambda.
Good. Then go and calculate your wavelength. What wavelength you get? Tell me the answer when you get it. Yep. What is your first wavelength? Minimum wavelength or maximum wavelength? Ken, make sure you got your paper, calculator, everything, and pencil and pen ready with you when it comes for tuition. What's the answer? Yep. What's the answer? Why take so long? That's all. That's the largest, longest wavelength. 16.5. What's the smallest wavelength? Yep. Got the answer? Smallest wavelength?
Smallest wavelength, 320.
Yeah. 330 divided by 20,000.
Wait, not
16.5.
340, teacher. Why put 330 there? It's 340.
Huh?
It's 340. You put there 330, teacher.
What 48? Oh, I got it wrongly. Sorry. Sorry. You cannot change the answer. Sorry. Thank you. 340. So this one is 17.
Oh, looks like what's that? There is no 30-minute, 10-minute break, teacher. We still going on again. Come on, lah, just go on, teacher.
No. I'm not going to go on. I'm going to finish off any question to ask and then give you a short break. Don't think you can take 2 hours, 1.5 hours. So anything you want to ask, if not, we will stop
No,
here.
no, teacher. I'm okay. Just carry on, teacher. I'm
No,
okay.
carry on as I say. Revision
Okay.
also the video, half an hour, you just choose what video you want to listen to rather than having a problem selecting it. Anything to ask?
No, nothing yet.
Right? If not, I will stop here. If you got no question to ask, nothing to
Okay.
ask, then we'll stop here and then we will carry on 5 minutes time.
Okay.
Okay?
Okay.
We start in 5 minutes time. 9:46 now. We need another 45 minutes.
Okay.